In this video, we're going to work through a full example to find the behavior of a function and graph it by hand. Let's jump in. Okay, so here's the function. Go ahead, pause the video, and see if you can find each of these, the domain, asymptotes, intercepts, and any removable discontinuities for this specific function. Go ahead and pause and see if you can figure that out. Okay, so here are the answers. If you understand these and you're able to get these easily, go ahead and skip the video. Otherwise, stick around and we'll explain exactly how we found these. Okay, so let's think about how to solve this. The first thing we'll do is focus on the domain. So think about the domain. Basically, whenever we're dealing with any function, there's really only three reasons and practically two reasons in the vast majority of cases when a value would not be in the domain of a function. So the first one is that when we have division by zero. So we can't have division by zero. The second thing we cannot have is a negative inside of a square root. Remember, that would be a complex number, which if we're assuming that we're dealing with only real numbers, we can't have that. The third one is if you have a negative inside of a logarithm, but that's actually pretty rare, so that doesn't come up very often. So it's really just the first two that we have to watch out for. Now, in this case, we have no square roots, so that's not possible. So basically, we just need to find the values that would cause division by zero, and those will not be in the domain. So effectively what that comes down to is setting the denominator equal to 0. So let's do that. 3x squared minus 3x minus 6 equals 0. We basically want to find the x values where that happens. So here, the best thing to do is actually to factor out a common factor as much as you can throughout all of this. Then we end up with this. And again, you can factor it even further. So hopefully it makes sense that just by guessing and checking, you're looking for two numbers that multiply to -2 and add to -1, essentially. So hopefully it's clear that these are the numbers. And if we solve these, hopefully it's clear that x equals -1 and x equals +2 are the problem points. So what's the domain of this function? Basically everything except that. So the domain in this case should be -infinity up to the first problem point, which is -1. Can't have that, so we'll do parentheses so that we do not include it. Whoops. And then we can include all the values between the first problem point and the second problem point. So -1 to 2. And then we can include all problem points from 2 to infinity, basically. So there we go. That's why the domain is this for this problem. Okay, so in part B of the problem, we want to find any asymptotes. And specifically what we mean is vertical asymptotes and horizontal asymptotes. We could also have, well, I'll just say we could also have slant asymptotes. That's not a factor for this problem. So in this problem, we do not have any slant asymptotes. So I'll just focus on horizontal and vertical. But technically, slant asymptotes could come up as well. But anyway, it's probably easiest to start with vertical asymptotes. And when you're trying to find asymptotes, or specifically when you're trying to find vertical asymptotes, and also for later removable discontinuities, the best thing you can possibly do is to completely factor the numerator and the denominator for any rational function. So here, remember in part A, we already factored the denominator and set it equal to 0. So we already know that this is what the denominator is. But what we can also do, we can also factor the numerator. And the best way to do that would be first to factor out a 5, because every term is divisible by 5 here. So x squared plus, so you get x squared plus 5x minus 14 over 3 times x minus 2 times x plus 1. And we can actually factor a little bit further in the numerator here. So that'll end up being 5 times, think about it, what two numbers multiply to -14 and add to 5? X plus 7 and x minus 2. So there we go. That's how we completely factor the numerator. And then the denominator will still be 3 times x minus 2 times x plus 1. So there we go. Now, here's essentially the logic. If we're looking for vertical asymptotes, we are looking for places where the denominator is 0, but the numerator is not. And that second part is actually important, because you might look at this and you might say, we have a vertical asymptote at x equals 2 because the denominator is 0 there. Actually, that's not true. We actually have a hole, which is the next problem, or removable discontinuity. That's another part that we'll answer. because we have a factor here that's being matched in the numerator and the denominator, that actually means there's a removable discontinuity, or a hole, and it's removable because we could cancel them out. A vertical asymptote is a non-removable discontinuity that we can't get rid of like that. Now, again, the rabbit hole goes a little bit deeper here, because if you had something like this, for example, x minus 2 squared, you could remove one of them, but not the other one. So basically that would mean, if it was really x minus 2 squared, that would make x equals 2 a 0 of the function. And if you had a square down here, again, you could remove one of them, but you'd still be left with one. So if they have different multiplicities, you could still end up with a vertical asymptote there. But if it's the same factor and the same multiplicities, it's not a vertical asymptote. So actually, the only one that's not matched here that we can't get rid of is this one. So actually, we just have a vertical asymptote, I'll say. So vertical asymptote, or asymptote at x equals -1, because that's the only one that we can't match. So hopefully that makes sense. The next thing we want to work on is a vertical asymptote. Again, or sorry, a horizontal asymptote, I mean. And arguably, horizontal asymptotes are less work than vertical asymptotes if you know what you're doing. Basically, what you do is we want to take the limit as x goes to infinity, basically, and negative infinity. It's good to think through both, but I'll just focus on the positive case here of this problem. So think about what it is. Remember, when we're taking the limit as we go to infinity of a rational function, everything except the dominating terms don't really matter. So this is really just 5x squared over 3x squared. And again, I won't go into why that's true. I've covered that elsewhere, but when you're doing limits at infinity, it's true. And now you can see here, whether we're going to positive infinity or negative infinity, it doesn't really matter, because these are going to exactly cancel out, and we're going to be left with 5/3. So y equals 5/3 would be the horizontal asymptote. Hopefully that makes sense. Okay, so in order to find the intercepts, we need to find the x-intercepts and the y-intercepts. So it's probably easy to find the y-intercepts. Basically, if you want to find a y-intercept, you need to think about what that means. The y-intercept is where the function intercepts the y-axis. What is the equation of the y-axis? X equals 0, not y equals 0. X equals 0 is the equation of the y-axis. So here's the y-axis. That would be a vertical line at x equals 0. So basically what that means is, if you want to find the y-intercept, you basically plug in x equals 0. So in this problem, hopefully it's clear that if I plug in x equals 0, I will get y equals 0. Anything with x is going to be zeroed out, basically. So 0 squared is 0, plus 25 times 0 is 0, minus 70. And then divided by 0 squared is 0, minus 3 times 0 is 0, over -6. So basically, we're going to end up with 70 over 6. And again, the question is, could we simplify this further? So yeah, we definitely can simplify it at least a little bit. These are both even numbers, so they're both divisible by 2 at least. So if I divide them by 2, I'll get 35/3. And that, I think that's actually as much as we can simplify. You could also think of it as a mixed number if you want. Like if it was 33/3, that would be 11, and then you have 2/3 as a remainder. So it's basically 11.66 or 11 2/3, however you want to think about it. But basically, this is the y-intercept. This is the only y-intercept. So the only y-intercept will be 0, 35/3. And for y-intercepts, the x-coordinate of y-intercepts are always 0, because that's where the y-axis is. Okay, so that's how we find the y-intercept. How do we find the x-intercept? Remember, it's a very similar process. Basically, we set y equal to 0, and then figure out what x values would make the original function 0. Now, this original function is not so helpful to us, or it's not obvious. It's going to be a lot more obvious if you write the rational function in factored form, or at least as much as you possibly can. Remember, we've already done that on the last problem, so I'm just going to copy that in here. So basically, we're going to take this problem, we're going to take this factored version and set it equal to 0. So basically, what we're looking to find are any spots where the numerator is 0 and the denominator is not. That's an important detail. Because remember, like you might say, oh, at x equals 2, that should be a 0. Actually not. It will actually be a hole there, because it's a removable discontinuity. The only spot in the numerator that will be 0 is actually when x is equal to -7. So there you go. When x is equal to -7, that's when we have basically an x-intercept. So that will occur at -7, 0. And just like with y-intercepts, the x-coordinate is always 0. With x-coordinates, the y, with x-intercepts, the y-coordinate is always 0. So -7, 0, we expect to be an x-intercept. Okay, so if we're trying to find removable discontinuities, we've kind of already discussed this, but basically you're going to want things to be in factored form. So we've already factored it previously, so we don't have to redo that work at least. And basically, a removable discontinuity is any factor that you have in the numerator and denominator with the same multiplicity. So in this specific problem, hopefully it's clear that x equals 2 does that. So basically we have a removable discontinuity or a hole at x equals 2. Okay, so now that we've found all of these different properties of the function, so that we know the domain, the asymptotes, intercepts, etc., we can now get a pretty good idea, actually, of what this is going to look like graphically without having a graphing calculator. So first off, let's find the intercepts. So the x-intercept, we know we're going to have 1 at -7, 0, so right here. So that would be an x-intercept, and we know we have a y-intercept at 0, this is really going to be 11 and 2/3. So that's actually going to be way off the graph, but it'll basically be up here. I'm not drawing it perfectly. We know we have a horizontal asymptote at 5/3, so really 1 and 2/3, if you want to think of it like that. So 1 and change, so maybe like roughly like this. And we also figured out that that's the y-intercept, whether you go to the left or the right. Or that's the horizontal asymptote, I mean, as you go to the left or the right. We figured out that we have a vertical asymptote at x equals -1, so something like this. And we figured out we have a hole at 2. So specifically, well, yeah, I take that back. We don't know for sure what the point is, but we know we have a hole at x equals 2. So where would that be? It's going to be, again, we don't know exactly where it's going to be, but somewhere around here. So we already know that. Again, you could think about what function would go through here that has this behavior. We can already figure out quite a bit of it, at least the general shape. It would look something, again, this isn't perfect necessarily, but maybe something like that. And then down here, something like that. So it's, and let me draw it a little better. So something like that. So right here, without any graphing calculator at all, and again, we could choose other values as well. Like we could choose other values to pin ourselves down. So like we could plug in 3 to the function if we wanted and evaluate exactly what it equals. Plug in 4 to the function and evaluate exactly what it equals. But basically, even if we don't do that, we can still get a rough idea, a pretty decent idea actually, of what it's going to look like. So now let's see how correct we were. Okay, so when we graph this in Desmos, you can see what we have here. We do seem to have a vertical asymptote at x equals -1, so that's what we predicted. A horizontal asymptote at y equals basically 5/3 or 1 and 2/3, so that seems to be right as well. We have a 0, an x-intercept specifically, at -7, 0. We have a y-intercept at 0, 11 and 2/3, if you want to think of it like that, or 35/3. So all of those are correct. And we should have a removable discontinuity at 2 when x is equal to 2. So let's see if that happens. That's harder to see in Desmos, but actually, yeah, there you go. When I go over 2, you can see how it changes to a hole. This is one limitation of Desmos that I've seen that I wish was a little bit different. I wish they basically made it more obvious where the holes were. Here, you have to actually know that there's a hole to even go looking for it. But yeah, we can see that, yeah, at x equals 2, there is a hole there. So that's a removable discontinuity. So in terms of function behavior, we've basically predicted exactly what it looks like. So hopefully that makes sense. If you have any questions, be sure to leave it in the comments. Otherwise, I'll catch you next time. See you.